Hello, everybody, and welcome to Handmade Hero, the show where we code a complete game live on stream. Today, I guess I don't really know what we should be doing today necessarily, but I think today what we will do is we will go hunt down some bugs and possibly play a little bit with how we're submitting primitives. Because I don't necessarily want to start today on sort of the shaders, multi-sample buffer sort of stuff. We're going to have to upgrade the OpenGL part. For right now, I was only using, a slightly extended OpenGL to the old school one that's, that you can just link to on Windows and run. We only query a handful of extended functions, and those were both basically only for using sRGB instead of, to basically to have light linear color operation. And so we were doing that very specifically because I didn't want to teach a bunch of OpenGL minutia if we weren't necessarily going to use it, but we probably are at this point. So it's a good time to go, all right, let's take a look at how you initialize OpenGL in a more modern way where, we're going to load a vertex shader and a pixel shader at least. Possibly not. We could even use more shaders at the head end, like geometry shaders and stuff like this, in order to produce our sprites instead, send down more compact information for our sprites, for example. We could do that. I don't know that we will or should, but we'll sort of do that work, and we also need to, because we are actually using the Z-buffer now, we need to go ahead and use some slightly more advanced features like multi-sample anti-aliasing and alpha to coverage, just to make sure that we can do the least amount of on-CPU work to get our sprites sorting properly. And again, a lot of this stuff is just to eliminate visual artifacts of compositing alpha-blended 2D sprites. You can see them how it is at the moment. You can see a lot of this stuff here with the Z-buffer and the fringing and that sort of stuff. That is what I'm talking about. We need to eliminate those for visual quality purposes. Everything else is fine for our purposes in terms of Z-buffer wise. And the only other thing that I thought we were going to have to do is because our sprites are stacked on top of each other at such an oblique angle, or I guess steep angle, I don't know what you want to call that, at such a steep angle, we're going to have to potentially fudge the z-coordinates so that things rise up out of the plane faster than they would in geometry terms when they're accessing the z-buffer. So that's basically like the last set of stuff we have to do to move over to 3D and to get visual quality. And get rid of like the flickery bits and the fringing. That's really what we have to do there. And what we can do is we'll try to coincide that with updating to the new art as well. Basically, the holdup on that is I have to go process it out of Photoshop and put it into like our format and stuff like that, which is kind of a bit of work for me on the side. But that's really what we have to do for that as well. So that's really all we are looking at here. That will not be particularly difficult work at all. It's just time consuming because anytime you're working with sort of a black box in like we are with OpenGL, where we can't step directly into the code, we are at a severe disadvantage for obvious reasons. We aren't able to easily track down bugs we might have because we can't watch what happens to things we send down the pipeline. So, if you take a look at something like multi-sample anti-aliasing, we can go through the special magic mojo of turning it on and resolving our buffers and whatever. And, maybe it works. Maybe it doesn't work. If it doesn't work, how do you solve it, right? And so you have to kind of go through this process of like sending down structured art and looking at what happens to it and making sure that it verifies and that sort of stuff in order to really be able to get well-working programs here. So we may also at that point have to switch to a different computer. The reason for that is just that one of the things that aids debugging greatly with something like OpenGL is having the ability to use one of the inspection tools like Nsight or one of the other tools that allows you to look at what your OpenGL instruction stream is doing. And I mean, we could try on this machine to do it, but I'm not optimistic that we will get any of them to work. We certainly can't use Nsight because it's got an AMD card in it, but I don't know that we'd even be able to use, I never remember the name of, there's a public, there's a non-vendor specific one whose name I always forget, but that would work on AMD cards, but we can't probably use that one either just because the graphics card on this machine is so old that I would be surprised if the tools can really work on it effectively. Because it's a graphics card from 7 years ago, and I just don't know that anyone's bothering to keep anything up to date on that. So if I knew what it was called, I would mention it, but I'm assuming that if we tried that, it wouldn't work. And fundamentally speaking, it's not generally a great idea to do development work on old hardware anyway, just because, again, you're making life a little harder for yourself. The time to play around with older hardware is when you're getting closer to shipping and just want to do compatibility work, not when you're trying to get stuff working and you're fighting the hardware in addition to working on the new code. So, all that being said, we pretty much finished the cube stuff. We don't have any textures to put on the cube. So I'm going to go ahead and just start some debugging and start some refinement of this. And next week, because I'm assuming we'll have enough work to do today of just kind of going through that stuff, that we won't have to start with the OpenGL stuff. But maybe we could do the multi-sample buffer. In fact, I guess one thing we could do, if we wanted to, was try to turn on multi-sample anti-aliasing today, because that would be separate from loading any shaders or anything like that. So we could try that as well. In fact, maybe that's what we should try. We could try that in alpha to coverage. So maybe let's do that. I'm going to go ahead and turn off the textures. Let's go ahead and do that here. Since we don't have a texture for the cubes there, and it's going to be a little distracting to have that, that sort of nonsense in there. So I'm going to go ahead into OpenGL, the renderer portion of the OpenGL renderer portion of the code. And I'm going to go ahead and take out the texturing. So all I'm doing is I'm placing a disable at the top and an enable at the bottom. And again, since this still is using the fixed selection pipeline, at least until next week, we can still monkey around like that. So this is the cubes being drawn just with a white color, obviously. What I'd like to do here is, again, since we're just hacking something in so that we can see it okay, and we will kind of deal with this when we get to the new art, we can fuss a little bit more with how we want to specify our cubes. What I'm going to do here is something a little bit bizarre. You can see where I've got this, this P0, P1, P2, P3 stuff here. We created this to talk about our cube. We can see that there's these negative z points. The 4, 5, 6, 7 are all points with the lower z value. The 0, 1, 2, 3 are all the points with the higher z value. I'm going to go ahead and just do a couple kind of bizarre things here. So, and this is just to get something visually reasonable that we can use. And I'll explain a little bit about what it is. I just want to set it up first and you can see it. And it's just a way of sort of getting something that you can look at that'll be sort of a little bit more of a proper cue, proper visual cue. So if you take a look at what's going on here, we know that everything that's a P0 through 3 is the top face of the cube, right? And so you can see here this GL quad, this is the top quad because it's P0, 1, 2, 3. And those are all ones that have positive Z. So we know they're the top faces, they're the highest up faces. So what I want to do is I just want to make the top of the cube. I'm going to just change this so that instead of it being colored by these sort of random colors I put on here, I'm going to make that be this thing called top color, right? And then what I'm going to do is I'm going to assign the rest of these. So we know the bottom one as well, we know, right? It's 4, 5, 6, 7. So we can see here 4, 5, 6, 7. This is the bottom cube. We could have a bottom color of our cubes as well, although for our present purposes anyway, we can't see that. So the bottom color is largely irrelevant for all of our actual purposes here. So I'm going to set the top color to the pre-multiplied color, the bottom color to nothing, just black, and no alpha. I guess, well, you know what, I'll make it actually solid black, so I will give it alpha. And then we'll have that primo color. And then what I'm going to do here is I'm going to make a gradient on the other sides of the cube. Now, again, I'm just going to make these, instead of like this C0, C1, C2, C3, I'm just going to make 2 of those, like so. And what I'm going to do here is I'm going to say, all right, for the C0 one, I'm going to want a color wash. That whatever the top color of the cube is, I'm going to have that be the brightest version. So when the person specifies that they want a cube of a certain color, they're going to get that on top of the cube. Then on the sides of the cube, I want a dimmer color, and I want that color to get dimmer the lower it goes. So it'll start out a little dimmer than the top, and then by the time it gets to the bottom, it'll be much dimmer. Okay. And so what I'd like to do there is I'd like to say, okay, whatever the top color's RGB was, right? I want to dim that down a little bit. And I'm going to keep the top color's alpha value. I guess I should do it this way so that you can specify transparent cubes if you really want to. So basically, I'm just going to take a gradient here by saying I want whatever the top color was. Oops. I want 75% of that, so just make it a little darker at the top, and then 25% of it at the bottom, so much darker. And I'll use the CT and CB for that. And then I'm just going to look through here and say, all right, so I know 0, 1, 2, 3 are the points that are at the top. So I'm going to call that color top. And I'm going to call the other ones color bottom, right? So basically 4 and 5, which we know are like down below on the bottom of the cube, they get the bottom color. And so, 2 is top, this is bottom, bottom, top, top, bottom, bottom, top, bottom, top, bottom, top, top. And then now we've essentially got a procedural assignment of colors to the cubes, okay? Now what you can see, hopefully, when I did that, right, is now we've got a way of looking at these cubes that's just visually easy to parse, right? It may not be useful for our final game, but we don't care about that at the moment. What it does is it cues the eye in visually to what's going on in a reasonable way. Like, we can read that landscape pretty well. And so if we want these to be grass-ish just for the current time, and again, this is not final art, this is at all, it's just because we're going to put whatever the artwork says we should put on there. When we create these guys and we add a piece on here, we can just specify, like, okay, we want some color value here, that's going to be some kind of a green. I don't know what that should be exactly, but there's a green. That's an awful green. That's probably the worst idea ever. Let's try to maybe make that more of a pure green. I don't know why I did that way. That's like too green. You know what? Why don't I just use color cop? Do I have color cop on this machine? I love color cop. Color cop's my favorite little color utility. So let's see what color green I want here. I think I want sort of a brownish green. All right. So color cop's great because the thing that I like about it is you can specify the mode, and you can say RGB float, for example, and it'll just like give you the correct values to paste into the program, which is like just a nice thing for a color picker to have. You know what I'm saying? So there we go. There's a color that'll at least be somewhat reasonable. Oh, but you know what? Those are not those are not alpha, those are not sRGB corrected. So in order to do that, I do have to convert them. So because these are linear colors, I believe. Oh, yeah, but that also converts to 255. Well, I guess this would do. We should probably make a function for this, because since we have to specify colors in linear space here, not sRGB space, we should probably make a way of inputting them properly in sRGB space. Still feel like that should be, just still feels a little too light. I want to see though if we've got that right. Come back to me, color cop. But we did get that right, so that was just, we just need that sRGB conversion there. And you'll notice I didn't really do sRGB conversion. I just did squaring it, because in the app right now we don't actually do a real sRGB curve. We probably should now that we're using OpenGL. In our software renderer, we decided it was too expensive to use real sRGB, so we just used a squared curve, which is, you know, close enough, good enough for government work, as they say, but not, it's not right, because the graphics hardware can actually do a more accurate version. Let's try this. Just a darker, maybe even darker still. I don't know. And let's go ahead and make that that math function too. So in this case, we want to basically make a result value here that's just going to square the values and give us our sRGB approximation, an approximation of un-sRGBing the sRGB inputs we would get from a program like ColorCop. So we just want something like that. So I can say, you know, sRGB linearize. And maybe we do one for extra added convenience, right? I could also say here, well, the reason we'd be using this in most cases is for a hand-coded value. So maybe we make an sRGB linearize that takes in R, G, B, and A, and returns the V4. And so then we can just do, you know, the input equals RGBA, the result equals sRGB linearize of the input, and then return that result. And so that is also kind of handy, because then we can sort of say, well, if we were going to be doing this, we can now just do this instead. And pass in hand-coded values, essentially. So let's go ahead and run that. There we go. And that's not particularly attractive, but that is what I want roughly for being able to see what's going on, right? And so I said I would explain what I was doing here and why. So the reason that this ends up being an easier thing to see, right, is because it sort of does a very simple approximation to what will often be how things will look in the real world without actually taking the time to figure them out. So let me give you just a little bit of an explanation of what was going on there and why that produces a more visually parsable result. Here on day 367. So on day 367, whoop, we are dealing with fake cube lighting. I think my Milton has gone into its can't read the pen mode. Hold on a second here. What? Where is Milton? There it is. There we go. So we've got something that looks like this, right? And what I was doing was saying, well, all right, I know that these things are going to be stacked on top of each other a lot, or right next to each other, right? So we're going to have a lot of situations where, you know, we've got things that look like this or whatever, and stuff like that. If we were to draw all of these at the same color, right, if they're all green or whatever, the exact same green, then we just get one big solid mass of color, and you can't see anything, right? That's when I did it, when I first did it with white. It was just a mass of white, and you can't see anything. So it doesn't give you any information visually. You can't tell what you're looking at all. Now, in the real world, if everything was flat white like that, you would still be able to tell exactly what was going on, and the reason is, of course, because of this. It's because of lighting. Light strikes these surfaces, so even if they were all the same material, the same white material, and had no defects on them, whatever, and were all exactly the same uniform tone, you would still be able to see it because the lighting would change so much across the scene. And so what did I do to try to approximate that, given that we didn't actually do any real lighting? And the answer is, if we assume that there's something up in the sky like the sun shining down on us roughly, then what we know is the amount of light reaching this surface is going to be quite high, right? The top is going to get most of the sun rays are going to hit it and are going to bounce off favorably towards us, right? Because if we assume a fairly typical surface, you know, if you look at the surface from the side, for example, and you've got sort of light coming in this direction, then it tends to bounce out, you know, fairly uniformly. It bounces maybe a little more up here and a little less towards the sides, let's say, a little stronger at the, you know, it bounces a little stronger at the exact reflection angles depending on the surface and stuff like this. But generally speaking, you know, the more light you're getting in, the more you're bouncing out for a fairly diffuse kind of surface. And then if you think about what happens on the sides, well, the sides aren't getting as much of that sun, right? Because the sun's high up in the sky, and the amount of light that's hitting these surfaces is less. So the sides, you know, should be darker. And if we were being even snootier, Mr. Snoot, with the snooting, and we were actually talking about the real like lighting from the sun, we would pick we would have sides that were brighter than other sides because the sun is directional in that sense, right? But what I did is I did more like a sky lighting, which is to say, hey, yeah, the sun in the sky is obviously a very strong point light source, but there's also overcast days, right? And then it's kind of more uniform where the light's coming from, but the light is still coming from the top, right? So anything that's facing upward and is exposed to the top is going to get most of the light from a big hemisphere of the sky, right? Meanwhile, the sides are going to get less because any given side, it can only see one part of that hemisphere, right? If you imagine looking at the cube like this, and here's my hemisphere radiating light down onto it, my sky, right? Well, this top surface can see the whole sky, right? It can see everything. But this can only see one little portion of the sky, right? You know, maybe like that. And so it's going to be correspondingly darker than the top surface. Does that make sense? So making the top a brighter color and the sides a darker color is a good way to start approximating a skylight, a uniform, like sort of irradiant gray skylight, like an overcast day. And then what I did furthermore is I made them get darker as they went down. So I started with a value that was a little bit dimmer up here, but then when we got down to here, it was a lot dimmer. And why did I do that? Well, again, there's other things at play here. These are cubes that are stacked next to each other. And when cubes are stacked next to each other, they start to reduce the light visible to each other as they get deeper down, typically, right? So if I have something like this, where there's a valley here, as I get further down here, this will be occluding more of the sky from me. So it's just a guess that oftentimes as things get lower, there's more stuff blocking them, right? None of this is accurate to any kind of simulation of our scene. I have done no actual lighting. But what I did is bake in the way that lighting normally would react in an average circumstance, right? Something that sort of does a visual effect like that, and we get something that's easy to parse visually. Would you want this to be your final lighting? Absolutely not. And why not? Well, you want it to be more accurate to what's actually going on, right? What we'd like to do is have our lighting take into account the fact that, you know, here is a big tall edge next to a lower edge. There's probably some light getting removed in this area, right, from this blocker. So you know that things should get dimmer in here. And, you know, maybe we want some of that directional sunlight as well, right, you know, to give it some kind of more color. So there's, you know, if we wanted to do real lighting, even hacky real lighting, there's a lot of hacking we could do there that would produce better results. So this is by no means how you would want to do lighting in a real game. But in terms of just a quick way to get something you can visually understand, which is exactly what I needed in this case, you know, that is a really good way to do it, right? Okay. So now we need to move on to the main event, which was the multi-sample anti-aliasing. This is one of those things that you do like once and you forget about it, oftentimes, unless you're a rendering guy. So this is one of those ones where we're going to have to crawl through the documentation to find how to turn it on in the first place. But you know, I can explain the basic idea, because that's not so hard to understand. Going and finding the right magical incantation sauces in OpenGL and so on might be a little bit harder. All right, so let's talk about MSAA and multisample. I've lost pressure control again. I don't know. I feel like Milton, when you switch away from it, oftentimes loses pressure control, but I'm not sure why. Did it? No, it didn't. Oh, and I switched back and it came back? Interesting. Huh. I feel like there's a easy to resolve bug there that if you could just watch what was happening, it would be easier to find. Because it was just off and then it came back, which is kind of interesting. All right. Anyway, so multi-sample understanding. And I got so distracted by that I wrote the wrong thing. And alpha to coverage. All right. So what do these terms mean and why do we care? MSAA, you may, even if you have never programmed with it before and have no idea what it would mean in the graphical context necessarily, you may actually also already know what it means because it gets discussed very frequently in terms of gaming and graphics cards and stuff like that. So you may actually have already learned it and know what it means anyway, even though you never dealt with it in a programming context. Alpha to coverage, probably not. That you've probably only heard of if you've dealt with it in a programming context. But multi-sample anti-aliasing. Obviously, the term anti-aliasing is something that we've talked about on Handmade Hero before. Aliasing is a general term. It comes from signal processing, I believe, right? And aliasing is basically when you are getting sort of like an error in discretization. and maybe I'll say an apparent error. And so what this basically means is, if you imagine, let's say in audio is a very common example of it. If you imagine you have a sound wave or whatever, and you're trying to represent this sound wave that's an actual continuous thing in the real world, let's say, well, continuous is hard to say given that we have molecular and quantum things and whatever, but at the degree to which humans can perceive it, there is no aliasing, let's say. And so we're talking about something that we're introducing as an artifact. If we are to sample this at regular intervals, right? Then what ends up happening is at those regular intervals, you may end up producing a curve that is nothing like the existing curve, right? And so what ends up happening is when you take something continuous and you turn it into something discrete, like we have to in computing usually, you end up with the possibility of creating artifacts, and apparent errors that are apparent to the person who's using whatever it is, trying to listen to the audio or view the graphics. You end up introducing error that has nothing to do with that has nothing to do with how you're actually simulating anything internally. You may be doing everything right. It's just when you actually get to the point where you need to display it somehow or put it out the audio speakers, you only have a limited number of sample points to work with, and when you produce those sample points, you end up with this error even though they're accurate, right? Like even though we're talking, when I sample this curve, I didn't sample it wrong. I sampled it exactly where it should be, but it just isn't enough information. I needed like all these other points in here to capture the peaks and troughs, and I just didn't have a high enough sample rate, right? This is called temporal aliasing, by the way, which is when you have an aliasing artifact in time, right? Because here's time, here's amplitude, right? My sound wave. The same sorts of things happens in graphics, and it happens in graphics when we discretize to the pixel grid, right? We've got these pixels, and I want to draw a triangle. Well, the triangle is just like our audio waveform over here. The triangle has infinitely precise edges we can describe in mathematical terms. That is what we're actually trying to draw. However, when we go to convert those infinitely precise edges into actual discrete pixels, a number of discretization steps occur. First of all, we only have floating point, which is not infinitely precise. That's not that big of a deal. It is still precise enough. These days, floating point is plenty accurate for our purposes. In the old days, when it was fixed point, this was something that was much trickier, obviously. But so when we're using floating point, we know that we're going to get a very accurate location in terms of pixels. So no real harm there. But then when we actually go to rasterize, at every given pixel, if we only wanted to produce that much of a triangle, but we have to make a decision as to whether to fill this whole pixel or not, you can see how we get the same kind of aliasing artifacts. Maybe we decide to fill this one, right? But we don't decide to fill this one, and then we do decide to fill this one. You get these like stair-steppy little like crispy pixel patterns on the edges, and nobody likes that, right? That is not a sexy thing to see, these crispy little, sort of hard pixel edges as you go. So that's the aliasing that we're talking about in terms of MSAA. So anti-aliasing, obviously, are techniques designed to combat the objectionable visual artifacts that are produced from this process of discretizing to whatever. It could be, audio or the grid or whatever, but anything where the regular sampling destroys, or just sampling in general, sampling of a signal with more precision than the sampling produces objectionable artifacts to the viewer, listener, whatever. So anti-aliasing, obviously, techniques designed to prevent these aliasing problems from being apparent. Obviously, we can't increase the pixel resolution. We only have whatever resolution the monitor has, but we can maybe do things to help improve it. Now, what we've done in Handmade Hero so far is to do our anti-aliasing. What we do is we say, okay, let's just say that in the alpha channel, right, we're going to encode RGB A. In the alpha channel, let's go ahead and encode, rather than just an RGB value that says what the color should be when we're dealing with stuff, let's also encode a value that says how much of the pixel we were trying to cover. And the way that we did that is we said, let's have a sprite, and the sprite's going to have the graphics in it, and all around the edge of the sprite, the alpha values will indicate how much was covered there. This way, when we draw the sprite to the screen, we can blend in just that amount of color that sort of simulates a pixel being shared between the sprite and what was underneath the sprite, right? And that's how we got those nice soft edges, right? But now we can't do that same technique anymore. Why? Because that requires us to sort. In order to do that technique properly, we would have to sort our sprites, and the whole point is we don't want to sort them. We don't want to know what order we draw our sprites in. We just want them to work. Okay? So what we'd like to do is have a technique that allows us to draw in sprites where we're saying that we only cover a piece of a pixel sometimes, but have that still work, right? Well, it turns out that 3D graphics cards have to handle not necessarily this case as their primary case, but a different case that's related. And the case that they have to handle is exactly this one, right? Most of the time, when we talk about multi-sample anti-aliasing, as we'll see in a second, what 3D graphics cards are trying to solve is they're trying to solve the problem of drawing actual triangles. Because remember, we are drawing sprites, but 3D graphic cards are more about drawing shapes, right? And yes, they cover those shapes with actual textures and stuff like that, but a lot of times they don't have alpha necessarily. They're solid in terms of the texturing on them, and the part that gives them form is the fact that there's, you know, millions of triangles making up the actual shape of the thing that somebody modeled in MudBrush or whatever, right? MudBrush, that's good. I combined Mudbox and ZBrush into one tool called MudBrush that doesn't exist. Sorry, someone modeled in Mudbox or ZBrush. Or MudBrush, the new tool for modeling 3D. All right, anyway, so what they have to do is they have to try and figure out how to get rid of those crispy edges of the triangles themselves. What that means is they need, and again, they're dealing with exactly the same problem we are in terms of the aliasing, just not with sprites. They've got the same problem of the edges, and they also don't want to sort, right? They don't want to try and sort triangles in sort of the GPUs that handle anti-aliasing this way. They want to be able to draw the triangles in whatever order they came in, and then still get a reasonable result for a pixel where a triangle only covered part of it, and more specifically, perhaps where many triangles crossed, right? Like maybe I've got multiple triangles coming through a single pixel, and each one only is covering a certain place, right? And I still want something reasonable to happen here, right? So the way that graphics cards handle this is, well, there's been multiple techniques over the years, but MSAA is the current technique that is mostly used. It's multi-sample anti-aliasing. What it means, as its name implies, is rather than only tracking one Z value, Z buffer and color value, depth buffer and color value, for a pixel, let's distribute some samples in a pixel and track them all, right? And this is when you see 4x MSAA, 16x MSAA. You've seen these terms probably. The number plus the x, what that's telling you is how many samples we're talking about. So if I'm doing 4x MSAA, it means that for every pixel, I've got 4, points in that pixel I'm actually tracking. What that means is that when I have something like this case, now I know, okay, this triangle here that passed through, it colored this pixel and this sample and only this sample. So this sample was actually filled right here by this triangle A, let's say, right? This triangle B hit this one, right? and this triangle C hit these. Now A and B, A also hit this one, and B also hit this one, right? So we still have the same problem at our samples, and whichever one had a z-buffer value that was higher will be the one that wrote into this location. So it's not like it does the blending properly at the samples. It does the same problematic non-blended. It doesn't do order-independent blending at the samples. But now we don't necessarily care, because now we can produce a blended value that we know should be 1/4 A, 1/4 B, and 2/4 or 1/2 C, right, at this pixel, because we only have to output a single color for the pixel. And so now we've sort of reconstituted a proper order-independent blend out of order-dependent samples, right? So that gets you out of the sorting business so long as the number of samples you need is not too high. Now remember, in order to produce the exact same output as a blend would produce, we would need 256 samples. Why? Because there are 256 levels of color in our output. Now that's getting even worse. UHD or, well, I don't remember what they call them, but the new displays that are HDR, high dynamic range, and can support, 10-bit, 16-bit color, any of these sort of higher color depths, then even 256 is not enough. This would have to be 65,000 samples, right, to reconstitute a value like that. But chances are, if we're only talking about just the edges of things, this amount of blending, 4 samples or probably 16, if we're going hog wild, 16 times over sampling is definitely going to be sufficient to produce just a reasonable soft blend at the edge, right? Because we don't need the full 256, we don't need that precise of alpha blending at just the edges. Other things might need it, like smoothly fading in and out stuff wouldn't work because you'd have only 16 steps of fade. So it would have to be a fade that occurred over at a speed where 60 frames a second. It would have to be, so at 60 frames a second and 16 of these, it would have to be something that covered 256 in only 16 steps. So it would have to be fading at 16 color values per second, right? Which per frame, right? And so at 60 frames a second, that would be what? 960 a second. So something that went from 0 to 1 color-wise in a quarter of a second, roughly, right? And so something fading extremely fast would work okay because you wouldn't be able to perceive the difference there. But in general, something that was supposed to be smoothly fading in and out, it's not, going to handle it. You're going to see that step pattern as you get, multiple frames and they all resolve to the same value because you've only got 16 values to resolve to, and then it would stop down and stop down again. All right, so multi-sample anti-aliasing, that's all it is. That's it. And so all we have to do, is basically wade through the OpenGL mumbo jumbo to turn it on. But that's all we really need to know about in terms of sampling. It's that simple. So what typically happens, the way that this is set up in terms of GPU APIs, is what you do is you say, okay, create a target with MSAA, right, to render to. Then you render to that target, and what it does is it renders all of the samples. So it's a lot more expensive. It's 16 times more expensive in terms of number of pieces of information it has to fill. It's not 16 times more expensive throughout the entire pipeline because a bunch of stuff doesn't change. Like the triangle setup phase, like vertex shaders don't have to change. This is only a pixel operation, but it makes your pixel operations a lot more expensive potentially, right? And there's things you can do to mitigate that. In our case, like we don't have complicated shaders. Maybe we will eventually, and we'll have to think about this more. We don't have complicated shaders right now, so we don't have to worry about our pixel cost as much. But you can imagine if you have very expensive shaders, this is where stuff like deferred shading, right, starts to become even more important, because now you're talking about 16 times more pixel shader evaluations that are happening there. And so oftentimes what you want to do is make sure that you're only actually executing those for the final Z people. So a Z prepass or deferred shading, these things get more important as you start cranking up that pixel count. But anyway, so then you render to that target, and that renders 16x more pixels, basically, more pixels. But the reason that we don't call them pixels is now should become apparent to you finally, because we've often used the term fragment, and it's like, why are they called fragments? Well, oftentimes they're not actually pixels that we're rendering, right? In this case, now you can really see they are actually these little samples. So the phrase fragment is just what OpenGL uses to say, hey, depending on how you've got your rendering set up, we don't know that this has anything to do with pixels. So calling this a pixel shader is not right. It's a fragment shader. It produces basically point sampled color values, but we don't know how those are going to be used. They might be output to pixels. They might be output to samples. There could be, so it really is this sort of other idea, and it's sort of a stage of the output that we don't know exactly what its end use is going to be. When we're talking about it, it could be any number of things you want to do with it. Hence, they invent the term fragment to refer to that more specifically. Anyway, so we create a target with multisampling. We render that target, and then there's a thing called a resolve. And the resolve pass is just a pass that says, all right, at some point, I have to take these multiple samples. I have to crunch them down into an actual pixel value. So I need to go from 16 samples to 1 sample. How am I going to do that? And the answer is with the resolve. The resolve will take that target, and it resolves the target to the output buffer, to the actual display buffer. And you have some control there, right? You can do, because you might want to do different things with you might want to, depending on what kind of rendering algorithms you're using, you might want to do different things with the multiple samples that you have. We don't, because we want to do just straightforward anti-aliasing. Like all we're doing is trying to do the very basic anti-aliasing. But you can imagine whenever you introduce features like multisample anti-aliasing and other things like this, the people out there who are trying to do the photorealistic renderers, or like the new Doom engine, or the latest version of Unreal or whatever, they are constantly trying to use these features to do all sorts of advanced graphical things. So, you don't want to pre-tell them how they have to resolve their samples, because if you allow them a little control there, they can get more mileage out of their algorithms and do more stuff with these than just simple anti-aliasing. So MSAA, we're using it for literally the way it was designed. Just take multiple samples, blend them together, output them to the screen, get us some basic edge anti-aliasing in an order-independent way. That's all we're trying to do. Not super complicated, but you can understand why that sort of thing is a little bit more programmable in certain cases where you want to have more control there to do more advanced rendering things potentially. So this is all we have to do for multisample anti-aliasing, but as those of you, as the sharp, independently motivated viewer will have already noticed, I'm sure, if you actually take a look at our pipeline, we did not address a very important aspect, which is where are we getting the coverage information? Because this is how they're getting the coverage information in the case of triangles. And so if you take a look at what was happening here, and I gave this diagram of having 4 samples in a pixel, and some triangles come through, and you can see which triangles cover which samples, and so that makes very good sense how you would render these. We don't have any such information. We are not drawing any triangles. We are drawing sprites that have big areas of coverage, and it's inside the primitive itself, deep inside the primitive itself potentially, where the value actually is. And it's that alpha channel, right? It's the alpha channel that's telling us where that's coming from, where the coverage is coming from. And so that's where this other technique comes in, which is called alpha to coverage. What alpha to coverage does is alpha to coverage says, let's read the alpha value and pretend the alpha value says which percentage of these samples are covered. So if I see an alpha value of 1, I know that all of them are covered. But if I see an alpha value of 0.5, I know that only half of them are covered. And so I'll fill in that number. Now, at this point, we get to a sort of finesse element of this technique. There's a tremendous amount of subtlety in knowing where are the samples. Because if I take a pixel, right, and I say this is 4x MSAA, it's like, well, okay, if it's 4x MSAA, I could just make it be like a subgrid of pixels, right? I could just divide this pixel into 4 pieces, 1, 2, 3, 4, there's my sample, right? Or I could randomly distribute them around, right? In maybe like a blue noise-ish kind of fashion. I could do more of a white noise fashion or whatever. Any of these, all of this still easily comports with the notion that I've got 4 samples inside a pixel somewhere, but it's not at all clear, you know, how to distribute them. Furthermore, if I've got 2 pixels next to each other, there's nothing to say that I couldn't distribute these pixels in ways that are designed so that when I compute the value for this pixel, maybe I use a bigger region than the pixel itself. Maybe I reach into neighboring pixels for part of the values, right? I mean, this is anti-aliasing after all. So there's a tremendous amount of finesse that goes into understanding how to get the most bang for the buck out of how the samples are distributed. And it may sound very difficult to pick arbitrary locations for how you put your samples in, right? You know, when we had pixels and they're rectilinear, it's like, oh, it's very easy to see how triangle fills them. How do I deal with it if it's like in these weird offset positions? How do I even do that? Well, remember, this is one of the big reasons that the sort of implicit surface rasterization version of triangle filling is very useful. Remember how we wrote ours, where we actually just took a rectangular region and we used the edge functions of the triangle to determine what was filled, right? Do you remember this? Well, that's the same technique you can use here. So when you actually write the rasterizer, you don't have to really do any more work. You just have, I mean, you do a tiny little bit. For your samples, you just have an offset that you know you apply to the x and y for that pixel, and then you just, everything else in the routine operates exactly the same, right? You just go ahead and offset those values to the jitter, whatever it is. It could be a regular jitter, it could be an odd, you know, sort of spread out jitter or whatever. And then you just evaluate the edge functions just like you would, and that tells you whether you're inside or outside at that point. So because of that sort of implicit rasterization structure, it means that it's really very easy to provide this additional feature on top, whereas if it was more of a pixel marching algorithm, it would be very difficult, right, to make that be efficient. What that means is that in a lot of cases, it's not hard to even allow the user to prescribe what this is if you wanted it to, right? Now, that's not necessarily super useful, but you can imagine just setting up tables yourself. However, it's important to note that oftentimes you want a pattern that changes from pixel to pixel, because if you don't do that, you can get aliasing again when things line up with however you've jittered your samples, right? And this gets into a lot of sampling theory that I don't really want to try to dive into at this point. But basically, you can think of it sort of as any regular pattern that you use in your sampling, there will be primitive structures that you will push down to try to render that will expose that pattern and show visual artifacts. So what you're trying to do when you design something like multi-sample anti-aliasing is you're trying to place your samples in ways that have no obvious visual artifacts in that way. This is where blue noise comes in. Blue noise is the most favorable pattern for placing samples in all cases. So, you know, a lot of times when you're looking at something like trying to produce the best sampling for multi-sampling aliasing, what you're trying to do is get as close to blue noise as you can without having to actually do the complete work of blue noise. We'll leave that for a different day. All right. So, given all of that, alpha to coverage, what that does is that says, all right, I need to fill these samples, and I've got some alpha value, right? And that alpha value in this case would be like 1, 0.75, 0.5, and 0.25, right? As I get up from 0 to 0.25, maybe I don't cover anything. From 0.25 I cover 1, 0.5 to 75, you know. Well, it's actually probably more like buckets like that or something, you know, who knows how you do it. But point being, you figure out how many you're going to fill based on how many samples there are and what the alpha value is, and you fill those in. But which samples? Right? And the answer is I have absolutely no idea at all. I have literally never looked. My blind guess is that it would use some kind of a function of the X and Y location of the, well, it couldn't use the X and Y location of the pixel because then everyone would choose the same ones for the same alpha value. But it could use the X and Y location of the pixel plus the alpha value itself to determine which ones it was going to fill in. But I don't really know. So I am curious. This is the first time I'll ever really be using alpha to coverage in any way where I care about it dramatically. And so I'm kind of curious where the OpenGL extension is for it to see if it even specifies, because it might not. Okay. Let's see. The built-in GL sample position contains the position of the current sample, right? The fine progress shader outputs. The built-in integer array GL sample mask can be used to change the sample coverage for a fragment from within the shader. The number of elements in the array is CL S over 32, where S is the maximum number of color samples supported by the implementation. So this looks like we would have to output it ourselves, though. So I guess there's no fixed function way to turn it on. So it does have sample alpha to coverage. But which extension actually introduced that value? Because it wasn't this one. probably was this one. Yeah, fragment coverage to color. So we want the opposite of that is the only thing. Come on, guys. Someone must have this in here. Well, somewhere somebody must have first proposed it, and when they did, they had to specify either how it worked or that everyone could do it differently. And I just want to find wherever the first one was, but unfortunately, well, okay. Where are attributes sampled? That's probably not going to help us. This is not giving me the answer that I want. I just want someone to show me the extension for this. I feel like that shouldn't be that hard to find. Right? I mean, shouldn't that be pretty easy? I feel like that should be pretty easy. Well, maybe we'll just have to let it not be known until next week, because I don't really feel like spending too much stream time trying to find it. But point being, somewhere, somebody at some point will have had to have said how it determines which samples to cover. And I'm not sure what that, if that is specified in a rigid way, like if you're implementing OpenGL, you have to do this, or whether it's more ad hoc, where they're like anybody who wants to implement something that does something reasonable can. So it's just the idea is it just has to cover this many samples. It doesn't matter which of the samples are covered. So that's, I don't know. You can see why it would matter, because if you have two sprites that are covering the same square and they both have an alpha value of something, you want to know what happens. So it's important. It's not an irrelevant situation. So I don't really know why there isn't. I was expecting to find, I guess it might have been because it's in, maybe because it's in OpenGL 1.3. Maybe it was introduced as this part of the spec itself and was never an extension, or maybe not. But if it was an extension, I can't find it, unfortunately. But, oh well. So anyway, that's the entirety of it. Notwithstanding the fact that I don't know where to find a definition of exactly how it chooses how to fill, that is what will happen. So, for our purposes, we need to be able to do all of those things, right? Some are easier than others. Obviously, GL sample coverage and enabling that is the easier of the two. So it looks like we don't have to use a shader for that. We can use the older version. I wasn't sure if there was an old version of alpha to coverage. I thought there was, but I never used it myself, so I didn't know if it was something that was only possible from a shader. Looks like that's not true. So when we're in here, we certainly can GL enable this and turn on exactly those values. We have to get them, obviously, but we should be OK. So if we take a look at GL sample alpha to coverage, we should be able to find docs for it, even if we can't find anything else here. This is not exactly what I want, but multisample, blah, blah, blah. I actually just want the set of enables for this. When multisample GL enable with argument GL multisample, a fragment mask is repeated for each fragment. That's fine. If conversion alpha as mask is enabled, alpha to coverage, fragment alpha value is used to generate a temporary modification mask, which is ANDed with fragment mask. Again, that's the part that I was trying to find the definition of, because we would like to know what that if there are rules for that modification mask or not. And off we go. After conversion of alpha values to masks, placement values is enabled. The fragment's alpha is set to the maximum allowable value. Not sure I get that part. After conversion of alpha values to masks, if replacement of alpha values is enabled, GL enable with argument GL sample alpha to 1. The fragment's alpha is set to the maximum allowable value. Okay. I don't think we actually need that. Finally, if fragment mask modification is enabled, GL sample coverage defines an additional modification mask. Oh, no, we do want that. I see what that's saying. Because we don't actually want blending to occur here, right? We're trying to not actually do blending anymore. So that takes the sample's alpha value and jacks it to 1 so that it won't do any blending. It's only using the alpha for the coverage. So we probably want all of those, right? So we want GL sample alpha to coverage. We want GL sample alpha to 1. And we want GL multisample as well. I think we want all of those enabled because they're all useful for us. So the only one we don't need is GL sample coverage. GL sample coverage would have us specify the mask more directly. So that would allow us to say, hey, we're trying to fuss with the mask for this drawing pass in some way globally, and we don't need to do that. So I think that's it for what we would need. I'm assuming these values are not present at the moment, but I could be wrong. I am not wrong. So we need to be able to get those. We can get those out of the GL core arb include. Here is all of these guys. I'll just grab them out and drop them in here. So that's all we need in terms of enabling those. This, again, allows us to turn this stuff on. So I believe that's all we really have to do to get alpha to coverage and multisample working in terms of telling the render, like the actual rasterization phase to do it. But that will not actually enable multisampling in our case due to the fact that we haven't set up a multisample buffer yet. So when we render this, we're not going to get none of those effects, even though we're calling GL enable on them. None of those effects are actually going to work because we don't actually have anything creating the buffer, the backing buffer for them. But hopefully that makes some sense there. What I did want to say real quickly is I believe we had a question about screen door transparency. And I just wanted to point out that screen door transparency and this are basically the same technique, right? Alpha to coverage is screen door transparency. It's just screen door transparency being done at a resolution higher than the screen resolution so that you don't see it as screen door transparency, you see it as blended color values, right? Because screen door transparency is basically saying, well, all right, I'll fill every other pixel with this render when I'm rendering guy 1. When I'm rendering guy 2, I'll fill the opposite mask, and then I'll get some transparency in there because you'll be able to see both of them, but you'll see it as kind of this stippling pattern. Well, if I do this but then blend these two together, right, now I don't see that stipple pattern anymore. I might see some discoloration that indicates the stipple pattern if I don't use enough samples or the samples are too regular. But again, it's basically just doing screen door transparency at a resolution higher than the screen resolution and then down sampling it, right? That's really all alpha to coverage does. All right. So we have to set up a GL multisample buffer, or I should say a buffer that's suitable for multisampling. And again, this is one of those things, like I said, I haven't done it in a real long time. So I'm going to have to blindly search for stuff to find our multisample. So I think there's two ways we can go with it. One way you can go with it is you can set up your main render target as a multisample render target. The other way you can go with it is just render into textures that are multisample textures and then leave your output buffer regular. I think we want to do the texture version. So I believe what we want to do is something like this. So you can see here, if you remember when we were, because we already did some render target stuff, we didn't do it for multisampling, but we essentially wanted to render to something that we could then use as a texture later. And you can see here me doing it. I bind a frame buffer and then I call GL frame buffer texture 2D and I pass a texture handle and say this is what we're going to render to, right? So what you can imagine is if we wanted to do the same thing, but we wanted that to be multisample, well, where do we create this texture handle, right? We call OpenGL allocate texture, which is a routine we wrote, and you can see right here what we do is we call GL text image 2D to specify a texture with some data, and that data just happens to be 0, right? So we just don't give it any data, so it knows, well, we're not trying to initialize this to anything, but here's what it is. So in our case, what we want to do here is we want to set up a multisample version of that. And so you can see that the way that we do that is we call GL text image 2D multisample. And in this case, we have exactly the same information, but instead of it being similar to a texture creation call, it can optionally be passed data. It can no longer be passed data, right? All right, so let's take a look at this call. We have the target, which is obviously just going to be the 2D multisample. We've got the sample count, right? We've got the internal format, which is going to be the same thing as it was. We've got the width and the height, and we've got the fixed sample locations. And the fixed sample locations is just saying whether or not whether the sample locations are dependent on where the image on where in the image you are, right? So yeah, I'm assuming that there's nothing specifically weird to this. I can't remember anything about it in particular. But I believe that's all we would really have to do there, and then we should be able to use it as part of the frame buffer. So I believe, I'll leave this page up. I believe that we can still just use the same call. Just making sure there's no other ones that I need to do. So I believe when we do bind frame buffer texture, let's load up OpenGL 3 there. I believe when we do GL bind frame buffer texture, we can use a multi-sample target there, right? The type of texture and the texture parameter for cube mask face to be attached. So I believe in this case, we should be able to do, gosh, there's a lot of stuff in here. Type of texture for cube mask texture, the face is to be attached. So I believe in this case, we can just specify the multi-sample one and we'd be fine, right? I don't think there's anything particularly bizarre about that. So I think that's pretty much all we would have to do to start turning on the multi-sample-ness of it all. But again, like I said, it's been a long time. I can't quite remember. So I don't really know if that's true. All right. So we also need to turn off our alpha clipping for this. We were previously doing a thing that we wouldn't draw if it was greater than 0. I guess, well, you know what? That can stay in because that's an alpha func that basically only kills areas we shouldn't be working with at all. So that can stay in. It was this one that would have been bad. So we have to stick with this one now for reals. All right, so when we're doing our max render target thing and we're calling OpenGL allocate texture here, what we're going to have to do now is change this to something that allocates a multi-sample buffer, basically, right? And what I'm not sure about, too, is when we want to actually do our final bake down, I'm not sure exactly how to set up the that resolve. OpenGL multi-sample texture resolve. Because again, when we've got this situation where we have our texture, which is the multi-sample texture, and we rendered to it, so now it has multiple samples in it, we have to be able to then render from that texture into a non-multi-sampled frame buffer and have that work properly, right? Let me see what the appropriate process is here. Let's see. Current specs is linear blit of that is not lay specs as a multi-sample resolve. I just want some good data here. Let me see if I can get anything. Blit frame buffer probably would be sufficient, but what if we want to read from them as textures? Do we have to resolve them first entirely? I guess I'll take a look at this first. There we go. Yeah, that shouldn't be necessary. I want to read from these as textures, and I feel like I should be able to do that, or at least resolve them without having to round trip through there. So that doesn't seem like what I wanted at all. So let's take a look if this has better. So this is exactly what I wanted, and this is exactly what I just said. So this all comports nicely with what we were talking about there. Once you've rendered your scene, you can display the annotated result of the scene by blitting your multisample frame buffer object to the back buffer using GL-blit frame buffer. So that is if we just want to display it, but what if I want to use it for rendering? Surely there is a way to resolve it into a texture, no? So I guess I don't know. I guess we'll try it this way first and see. I mean, one thing that is true is, so if GL-blit frame buffer is the only path that can resolve a multisample buffer, we still could generate textures with that, because since we are binding both frame buffers, right? If we're binding both frame buffers, then we should be able to, when we bind the read frame buffer, we'll bind our custom frame buffer that has the texture loaded. When we bind our draw frame buffer, instead of binding the default frame buffer, we could just bind another custom frame buffer that had our texture as a target, right? So we can do the resolve that way. Maybe that's the way they want us to resolve from a texture to another texture, but I don't really know. Like I said, don't really recall. But that is certainly possible, right? That would give us the ability to specify that that's what we wanted to have happen. What I would point out here is that since we're going to be going down this route, this also gives us the opportunity to get rid of some of the sRGB stuff potentially, because if we can get GL-blit frame buffer to do the sRGB conversion there, that would mean that we don't actually need to get an sRGB back buffer from Windows, which would eliminate some of the code on that side and would be nice, right? So there's that. So let's see here. Default sRGB Windows system frame buffers, non-blurb hardware loss blick solution, which is to pass, blah, blah, blah. No, probably not what I want. So basically what I want to know is, will blit frame buffer do an sRGB conversion if the two buffers are set up as such? I don't know if that makes sense, what I'm saying, but an application which passes nonlinear vector data. And by the way, you can kind of see, I mentioned at the outset of this episode that there's a bunch of black boxness to it. And I guess I'll just sort of drive that point home here. So again, this is one of the reasons that I find GPU programming so unsatisfying too, is that a lot of times, really mostly what you're doing is just spec jockeying. Like, it's not like I don't know what I would go write to write the rasterizer that did this multisample resolve, and I would know whether I was going to put sRGB in that resolve or not. It's very straightforward, right? But because it's this crazy non-orthogonal hodgepodge of like mushed together stuff, and all the graphics APIs are different, and all the GPUs are different, they're not really programmable hardware in the traditional sense. They're like spot programmable, right? You end up in this weird case of like you have to just hunt down all these special features all the time. It's really annoying because it's like, it spends a ton of time not doing anything that involves solving a problem. Like, it's not like I don't know where the sRGB conversion should happen. I would like it to happen there, and if I wrote that code, I could just go put it in. But instead, I'm constantly having to go like, oh, can it do it here? Will it? I don't know. Let me look at the spec. Okay, will that work on most hardware? Are there bugs there? Okay, maybe I shouldn't put it there. Maybe I should put it somewhere else. Can I put it somewhere else? Can I even put it here? I don't know yet. What if I enable frame buffer sRGB or not? Is that getting taken into account here? And it's just like, basically a complete waste of programmer time, right? At no point are you actually dealing with the problem. The problem is trivial. We already know what it is, and it's simple to understand and solve. So it's this really nasty, like, it's not, it makes me always, whenever I deal with it, really appreciate x86 and x64 as architectures where it's just like, look, here's the instruction set, here's what it does, write out whatever you want. Go nuts, right? And it's very easy to understand. It's very well specified. I know exactly what's going on at a given time, and it's really nice. Whereas with the GPU stuff, it is nothing like that. It's like most of your time is just spent figuring out the magic incantation to do something, whether that will work on the machine you're working on at all right now, whether it will work on the end user's machines, whether there's some other way of doing it that would have been more efficient, but you didn't know about it, you know? And it's just very unsatisfying. I find this whole thing to be very unsatisfying, and I definitely long for the day when GPUs kind of go away as a thing and it's just another programmable piece, but we're still not there. Maybe someday, maybe before I'm dead, although I am getting pretty old. So anyway, if we want to get started on this anyway, the blit here with the sRGB, I'm not sure what it will do, so we'll have to take a look at that a little more carefully. But for starters, we can certainly create GLText 2D multisample there. And also, we've got here on the OpenGL wiki, we've got an example of at least what the OpenGL wiki people think to be the right way to do it, and it is showing exactly what we were expecting here in this case. Now, for creating our drawable textures here, I'm going to stop calling OpenGL allocate texture and start putting this in line because in this case, I think we've got, oops. In this case, I think we want to start treating this very differently from our normal texture allocation case, because since it's going to be a 2D multisample buffer, it's going to be very different. In this case here, where we're taking the multiple samples, I feel like that's interesting. Why are we... Why are we not passing sRGB there? I don't like the fact that my head is in the way. I'm going to switch over to the side. Like, we've got this OpenGL default internal texture format. Oh, okay. Whew. All right. I got nervous there for a second. I looked at this and thought that that was the... I forgot that there's the internal texture format and the submission texture format, which are different. So that's fine. Okay. Sorry, I got real nervous there. So I believe we can just pass sRGB as the multisample format, and then it will still do the linear to sRGB conversion for us. We know what the width and height are. And we don't want regular sampling. We want irregular sampling because that'll give us less artifacts like I was talking about before. So I believe here we want a GL false value. And for number of samples, I guess for at the moment, we'll go hog wild and say 16, but I don't know whether this card supports 16 multisampling, to be honest. In fact, I guess we should probably call a GL get to determine how many samples it can actually do, or what its best sample type is. Because I'm assuming that there is a max sample. Here we go. So let's see. So I believe it would be GL samples. I don't know if that's actually true or not, but I'm going to go ahead and try to get GL samples and just see what it is so we can have an idea. Believe this is an integer. And I don't know that we've ever really done a GL get before. Have we? Yeah, we've never really done one before. We've never checked a cap. So OpenGL has a bunch of these GL get calls. And so you can kind of see how they work here, right? You say what kind of a thing you're trying to retrieve. So in this case, we're trying to get an integer, right? And the v is just because it's taking a pointer, so it might be numerous. Depending on which one you pass here, you might get back more than one. So I'm going to go ahead and say, max sample count, and I'm going to see what it tells me, right? Go ahead and get rid of all this. And so I'm going to say that we'll just ask for the max sample count at the moment, but maybe not if it's, we might clamp it. So I might be like, if max sample count is greater than 16, max sample count equals 16, because I don't want to go above that, certainly. And so let's try to get this path working. We'll just step through it. So in this case, we also need the GL texture 2D multisample define. Everything else I think we're good with. So in this case, we've got our texture handle coming back here. So I'll expand this to texture handle. Like so. And we're using get width draw region, get height draw region as the size of these. So I'll paste those in here. There we go. And so now all we need is to get the actual API stuff that we need for multisample and put it in here, right? And to do that, we're going to have to get the specification for these. And again, usually what I do for that is just grab them from the ARB. No, oops. Which I think I closed. Yeah. So I usually just go to the core ARB header file. And we need multi-sample texture, what was it called? Texture 2D multisample. So we really just need only this one. And then we do need the function as well. Oops. So here is GL text image 2D multisample. If we take a look at that saucy gentleman, we then need some place to, some place to put that, which usually goes in here. Although it looks like, do we not? Do we not have any OpenGL extension functions yet besides wiggle? Is that really true? Huh. We were pretty clean. That's interesting. But here's our wiggle get proc address calls. And so yeah, I guess that was all we actually did. Interesting. Well, either way, I'm going to start making some here that are in the OpenGL area because in general, we're going to want them on all the platforms, not just Windows. So the type def for these guys, which is the same kind that kind of comes out here, you can see I'm going to go ahead and start a place for these to get defined. And we'll call this GL text image 2D multisample as the type. And then we'll put in all of these things as they are. And then down here, we'll just say, OK, we've got one of those that is this function. This is a global variable. And now we can call it. Of course, it'll be set to 0 at the moment, which obviously is not the best thing to have it be set to. So we need to, in our Win32, we need to go ahead and grab the multisample. So I think that should get us initialized so that we can actually create the buffer that we need. But of course, we haven't actually done anything with that buffer yet. So we do have more work to do, as you'll see in a second. I'm going to go ahead and set a breakpoint in there, though, because I would like to, before we go any further, take a look at that sample value that's coming back and just see whether or not that function works at all. So I'm going to set a breakpoint here. And I guess we have to, before I do that, I'm going to have to force it. I thought we were still creating one extra sample, one extra layer, but I guess because there's nothing, because we got rid of that stacking stuff, there's nothing happening there at the moment. All right, so if that's the case, then I'm going to have to force it. I want this to happen with the max render target stuff. I want that to happen for the render targets. I need to create, even the first one has to create a render target, right? Which means that use render targets kind of has to work, if that makes sense. So we probably want to do here that says error dialog in platform layer if use render targets can't happen. because we're going to need that now, because if our entire pipeline is going to be based on multisample, we need to be able to create a render target, at least one render target. That's the multisample render target, right? I suppose I could try to get a multisample render target from Windows as the default one, but I'm pretty sure there's no such thing as hardware that supports multisample anti-aliasing via this method that doesn't also support render to texture. I could be wrong about that, though. So anyway, if we want to use render targets, we can just say that has to happen. When we use max render target index, we can now make that sort of forcibly happen. Although I think in this case, we don't really need multiple render targets at the moment anymore anyway. But where is global frame buffer count? So our global frame buffer count situation now needs to allocate the first frame buffer like it would allocate any of the other frame buffers as well, right? And so basically all of our frame buffers would be the same in this case, and global frame buffer count would start off at 0. When we bind these frame buffers, as we sort of go through them, we would no longer do sort of a differing set of these. We would always essentially do that in all cases, and then only when we actually, sort of draw the final frame buffer would we call the final GL viewport to the draw min, draw max, right? So basically, at the end of this, what we would have to do is this is where we would sort of do our final drawdown, and this is where we would do our GL blit frame buffer call. All right, so assuming that we're going to do that, now we should get forced into here, because even just having a 0th frame buffer, where we have one frame buffer, is sufficient to trigger it. In here, where I'd go get integer v GL samples. Oh man, does this card not have multisampling? That can't be true. This might not be the maximum sample count. This might just be how many are currently bound, if that makes sense. So let me, I'm actually interested to know. If I move this over here, does this do anything? Although that's not going to actually bind it. So let's see here. First transition status equals frame buffer incomplete. So we don't get a complete frame buffer after we have bound this. We did get a texture back, but that's going to happen regardless. When we called this, we don't know whether this actually worked or not, right? This might have worked or it might not have worked. So when we do global frame buffer handles, we presumably got one, and we did. So all of this looks like it's working properly, but the validation step does not actually work, right? And the validation step not actually working is probably because I tried to do the multisample bind. Oh, well, not necessarily. The GL frame buffer call here, we forgot to update it with 2D multisample, and that's required as well. So let's see how we do here. Not so good. Let's see what that status actually is. Hello? 36055. Well, looks like we're going to need it in hex, my friends. $8CD7. Incomplete missing attachment. So I don't know if that's actually true. Oops. Because we shouldn't need another attachment than that, should we? But if we can't actually create a 16x multisample, that might be sufficient to have that happen, right? Let's double check that there's nothing else particularly odd going on here. So you can see here's the GLGen texture call, here's the bind texture call, and the text2D multisample, right? And that's exactly what we're doing here. I don't think we're doing anything weird there, at least hopefully not. With the generating the frame buffers, that already got done up here, right? And so we're just going through and specifying them, and we're specifying them pretty much in exactly the same way that it's specifying them here, so I don't expect there's anything particularly weird about that. So the only question is really whether or not there's no way to create multisample on this particular beast. I'm not sure. I suppose we can check to see if it supports multisampling at all, but it pretty much, we know it has to, because if it didn't support multisample, then GL text image 2D multisample would not actually exist, right? Presumably, it wouldn't let us call GL text image 2D multisample on a card that didn't support any multisampling. I wouldn't think. It wouldn't have found that function, right? And if we take a look at our GL extension string, I'm imagining we could also verify that that was there. So if I go ahead and cut and paste this over into the scratch buffer, so GL ARB multisample is in theory supported. So I feel like, nope, that's not what I wanted. I feel like this should be okay, right? I don't see the actual extension here, unfortunately. GL max samples. That looks what I was looking for. Do we have GL max samples? Is that in core ARB? GL max samples. That's what I wanted. So it looks like I just queried the wrong value. But this doesn't help us determine why we were having the bug. I just really wanted to know what that value actually was, because I have no idea on this card. It's a really old card. I have no idea what it can and can't do. I'm totally no idea. So let's go ahead and put this back in. Max sample count. And it's saying that it has to be max samples -1. Is that implying that I need to bind a different texture for each sampler or something? Because that can't be true. But it says sample specifies the number of samples in the image and must be in the range 0 to GL max samples. So that sounds less like a sample count and more like a max sample number, right? Because if it was a count, 0 wouldn't make any sense. Like, you can't have a buffer that has no samples in it, right? So that's a bit weird. I don't really know what to make of that. But we'll take them at their word for now, since we're almost out of time anyway. And we'll maybe take a look at this in a little more detail later. All right. So I'm going to go ahead and take a look and see what happens at the max sample count. Query here and see if we can't actually get a value now. Switch this back out of hex. So here it seems that we'd have 8x multisampling, right? So our sample count's going to be 8 in this case. We're going to pass 7 to there, I guess, is what we're going to get. I don't know if that'll actually do anything. Like I said, we have no way of really knowing if that worked. And then here we get a status that we have insufficient attachments. But again, I'm not sure why, because we created a multisample buffer just like before. And I don't see anything particularly unusual about that, right? That all looks pretty straightforward. And it is in the color attachment, and there shouldn't be any requirement for us to put, we're going to have to put a depth texture in here because we do use the depth buffer now, but there shouldn't have been any requirement for us to do that in order just to get a complete frame buffer, right? That is not something we should have had to do. So I'm not really sure what the deal is with that. So a little bit of a stumper there. But I guess it's time to go to the Q&A anyway. So I'm going to have to leave it there, and we will have to pick it up next week. What would happen if I pass 0 here? So any call to GL text image 2D multisample is a bug as far as it's concerned. Can I replace that with a regular text image call? And get something reasonable? Oops. So it's only if I call GL texture 2D multisample that it is grumpy about I guess here's a question for you. And again, this is just not remembering very well. I wonder if what we have to do here is when we actually bind the texture, we have to bind the texture to the multi-sample slot. Right? Nope. Not so much. Although I am curious about that because it would seem like you should do that. Did they do that in the example? Yeah, they do. So I'm going to leave it that way. So if I do slot, and I'm just going to abstract slot away to here, right? So if I essentially make this code path work in both directions, then that would allow me, in theory anyway, to switch between the two paths pretty easily, right? So I can do GL texture 2D, or multisample now, and I just want to make sure that I can actually do that, right? So there's that path, which works properly, and here's the multisample path, which does not work properly. And we're not sure what it's actually grumpy about in this particular case, but at least now we've got both paths, so we can easily check them against each other. So I feel like this is the appropriate call structure. It looks like, now that I'm binding to the correct place. Bind textures, gen and bind. I don't assume you need, because again, they don't seem to suggest on the OpenGL wiki, on Chronos anyway, they don't seem to suggest that there is anything in particular you would have to do to generate one of them, because it's just a regular texture handle like everything else. You do bind it differently, right? But everything else is pretty much the same. And yeah, I don't really see any other. I don't really see any other fussiness there. It looks pretty straightforward to me, unless there's something wrong with calling these text parameter things. One thing I could ask as well is I could do a GL get error just to verify what was actually happening here. GL get error will tell me whether there's an error or not. So I can do GL get error in multiple places like this. And then what I can do is just say like, hey, why don't you tell me when the first time is that you saw the error, if there was one at all, and we'll go from there. What did you just to see if there are any. And so this is kind of what I would expect. You can see that we don't have an error, so I can actually bracket the error exactly and say, because I was guessing that the problem is our GL text image 2D multisample fails. So you can see right here, there is no OpenGL error at this point, but when we get to here, there is. So we know that this call failed, right? Our GL text image 2D multisample failed. Now, we believe we've got it okay because we're using a slot that's GL texture 2D image multisample. We're passing what we believe to be reasonable values, but hey, we don't really know. And so, you know, I guess it's a potentially open question. The default internal texture format, you know, we could try not asking for sRGB if somehow sRGB is messing it up. We can use exactly the syntax used in here rather than using sRGB, and I don't know if that's, I wouldn't assume that that would have anything to do with it, but you never know. Oops. What did I just do? First chance exception, access violation. What is the access violation? OpenGL render commands. So we're calling into this pointer, and it's got an access violation in ATI's driver. How is that possible? We're not calling anything. We're not passing anything. Right? I mean, all we're doing is calling text image 2D multisample. Wow. So basically, we can crash AMD's driver by specifying a sample count within the parameters that it gave us. Weird. So if I specify anything other than 0 here, nope, I can specify 1. How about 2? 2's okay, but 3 is not on the table, my friends. Three is just not on the table. So the instant we call GL text image multisample with 3, we are toasted. We are access violating. Presumably anything above 3 also fails. No. So 4 is okay. Five is not. So let's see if max sample count without the -1, which is what I would have expected to pass in the first place, is actually okay. And it is. So I think those docs are just probably a little misleading, it looks like. Because they said it had to be max sample count -1. It looks like it actually has to be max sample count unless ATI's driver is busted, which could also be true, I suppose. I'm guessing that that means that specifying sRGB as the internal format is not acceptable, because it seems like trying to specify that is just not working. I don't know what that means for us, because that means we can't have an sRGB back buffer in this case, I guess. I don't know. But anyway, I guess I will go to the Q&A now because we're over time already. At least now we know how this works. I don't know what is going on with that driver, though, because that seems real weird. That seems real weird to me. I don't know what you guys think about that. But that does not seem like proper behavior. I mean, far be it from me, I am not an OpenGL expert or anything, but that just does not make a lot of sense. Can you check if the status has changed after updating bind texture? Which bind texture do you mean? This one? Or do you mean the actual bind? I'm not sure what you mean by the bind texture. Did you remember to prefix your GL text image multisample 2D with a Win API, aka standard call prefix? I thought I did, but I might not have. Yeah, I did. Also, I don't think that would do anything because this is x64. I suppose this, in this case, I also... I also sort of have this problem of the renderer stuff here kind of, I guess, needs to be here because that Win API is a platform-specific situation, so I suppose I actually need that to be here. Oh, so no, we've got, so there's GL bind frame buffer. Where is that getting gotten? Win32 init OpenGL. Oh, so I put that other guy in the wrong place. That's probably not, that could be part of it. I felt like something had to be up there. So that was wrong, because we were calling that on the wrong, we were calling that in the wrong way. We were getting it before we had made the right context current. So I don't know if that might have been part of our problem. Let's take a look. Can we do this now? Probably not, but yeah. Oh well. Thought it was worth a shot. Masilda, your text parameter I needs to use GL texture slap between multisampling. Ah, yes, good. That's a very good point. I don't think that'll probably have anything to do with our current bugs, but it would cause problems in the future. These all always need to be slot. That should work the same as it was. Oh. Although it didn't. There is an error there. I guess, oh, you know, you probably can't set the filtering to linear on multi-sample buffers, I bet. Or maybe you just can't set these at all? Yeah, so it might be that you can't set these at all. No, there it is. Specified P name for target to the texture, GL 2D multisample. So I feel like we should have been able to specify those, but we are not able to. So I'm not sure why that is. Is there a way to debug or have a visual example of the multi-sampling process? I mean, you can sort of hack one together that draws like different parts of it to try and figure out what's going on, but not the way you might want. Not really, no. You kind of have to construct it yourself. Maybe we should use GL debug message callback and GL enable GL debug synchronous sometime. Then we can assert in the callback and we're able to just see where the GL errors in the debugger. Yeah, I agree with that, and probably we should, now that we're going to be doing more OpenGL stuff. I didn't bother doing that before because we weren't doing much with OpenGL, but now that we are, we probably should. Yeah, you can't set sample states. So I guess even we just can't set them at all. So we probably can set the clamping only. Or maybe we can't set the clamping even. So if we can't set any of those, then it doesn't even matter. I suppose, in that case. But yeah, that's kind of weird. I don't know why we can't set sRGB there. That's very strange. But yeah. Snoring Tortoise. You mentioned in a previous episode that one of the reasons for moving to 3D was due to performance concerns with the sorting. Would it have been a viable alternative to keep the sorting results in permanent storage and then each frame only resort the entities that have moved, just considering that many entities like trees and traversals don't move? I don't think it would be, and the reason for that is that I wasn't changing to ZBuffer because I was afraid about the number of sprites we had on the screen currently. I was changing it because I was afraid about how I would deal with the number of sprites on the screen I wanted eventually. And some of those things are like particle systems, right? Like if I want to have like thousands of particles on the screen or tens of thousands of particles on the screen, I don't want to sort all those, and those are all moving, right? So I don't think it's a very viable technique to use the sorting. I just don't think it's viable. I think there's a reason we don't sort things in 3D and unless we absolutely have to, and the reason is because it just doesn't provide enough performance. And it's very inflexible, right? Having to sort a primitive doesn't handle the case where, Painter's algorithm style break it, cycles and stuff like this. It doesn't really handle that properly because it can't split primitives either. So I think it's not just like the performance that we were getting was a problem, because it wasn't. We were running fast enough as we were. It's just there's so many red flags there for me, I felt like, that I didn't want to do it. So yeah, I'm confused as to why we cannot request an sRGB internal format for GL text image 2D multisample, and that is problematic. It could just be because this card is ancient. So I will probably have to order a new graphics card to plug into this machine, one that, is somewhat more modern, but. Mancelda says, Casey, I have started working on Handmade Vulkan port earlier today. Is that okay? Well, whatever backend you want to use. We don't have a whole lot of use of the graphics API in Handmade Hero, so presumably it wouldn't be too hard, but you're going to have to do a bunch of stuff to manage like getting the rectangle data down there, because you're going to have to actually deal with buffers and when they are used and stuff like that, which we don't have to do because we're going through OpenGL's sort of more straightforward does stuff for you pipeline. So yeah, I don't know. I'm curious. I'm really curious, though, if there's some other magic thing we're missing there. That's the reason why. So at least somebody else reports this having the same problem, but yeah. So alpha to coverage does order independent transparency just like that. Any serious limitations you can think of? Yeah, well, it's not really high resolution enough, right? So, if you want to turn on 16x multisample anti-aliasing, then, first of all, you're taking a big hit for that, right? And on Handmade Hero, we can probably afford it because we're not trying to do a bunch of complex 3D geometry stuff. We're just layering some sprites on the screen, and probably we could turn on something like 16x. But that's usually very expensive to turn on. So first of all, you get that. And then even if you turn that on, the transparency only has a resolution of 16 steps, right? At best. Probably less because you'll get collisions of the sort of dithering pattern, basically. So it's not really a substitute for sorting yet, right? It would have to have a lot higher resolution to really be a substitute for sorting. So it's more for handling the edges of things where that the number of alpha value steps is pretty low anyway, and you're trying to just get like a reasonable sort of pattern on the edge that's not going to be a harsh edge. I don't think we could lean on it to do stuff like actually transparent sprites and stuff like that, where we're trying to have like colored transparency and stuff like that at reasonable levels that fade in and out or stuff like that. I don't think it's going to be able to do stuff to that level of fidelity. But yeah, otherwise it does. For the limited case, it does handle it order independent. But again, it does have some real limitations. It's not an instant solve. It doesn't solve everything. Snoring Tortoise, for those of us who are very interested in engine development, what are some of the more advanced platform features that you would recommend investigating? Can you be a little more specific there? I'm not sure what that means. All right, it doesn't look like there's any other questions coming in, so I'm going to go ahead and close these down. I really wish we had some idea about whether this was correct or incorrect, that it doesn't allow multisample buffers in sRGB, because that's real weird in my opinion. I'm really not sure what to make of that. And the fact that we wouldn't be able to use sRGB there would be pretty annoying. I mean, we don't really need sRGB, to be fair. The only reason we ever did it is because Juan insisted that we do it. So I guess I would say I'm just not sure. If it's unreliable to be able to set a multi-sample buffer that's also sRGB, I'm not sure where that leaves us. And I don't even know how that could be unreliable, because all major games have to be able to do that. Everyone uses multi-sampling, and they definitely use sRGB. So I'm kind of confused as to what's going on there. It could just be because this card is too old, and maybe that's the reason, but it's just kind of weird. Snoring Tortoise says, on the platform side, like any debugging features, you mentioned a while ago that 1935 was light years ahead in that it is far more advanced. Yeah, well, so, I mean, basically, like, the thing to think about in terms of engine stuff is just platform layer wise, we do on Handmade Hero the stuff that we have to do, right? So basically we implement the features that we need to the extent that we need them. But it basically means that anytime if we were going to do something more or something different, we would have to extend or change how we were doing things, right? So, you know, if we wanted to write some code in the Handmade Hero, you know, using the Handmade Hero platform layer, for example, that did something like iterate over a directory tree somewhere and do a bunch of processing on the files there and stuff like that. It just doesn't really have that. You know, it has a very limited way to just get what our art asset files are, and that's like all it can do, right? So a lot of the time savings that we get on Handmade Hero for being able to implement stuff from scratch is because we do what we need to do and not a complete implementation of things that would handle a wide variety of cases. So if you want to create a platform for creating arbitrary stuff, you have more and more work that you have to do. So I wouldn't say there's anything in particular that like jumps out that's like, oh, you know, the platform layer that we use at Mali now is, you know, has this specific feature, and this is something that's important to look at. It's more the difference between the two is the one that we use at Mali now is designed to basically be the platform on which we build everything, you know, editing tools, tools for processing the art assets. It's designed to handle, you know, pretty much anything that you throw at it, so you can basically write everything to this platform layer and it always will work. And, you know, it handles Unicode and it handles, you know, there's no hard limits on path sizes. There's no, you know, so it's basically just like doing the engineering properly for anything just ends up being a pretty big difference in terms of what it can handle and what it can't. But I would not say there's any particular one feature or another that's like the thing that makes the difference between an advanced platform layer and a not advanced platform layer. It's more about completeness and lack of limitations, if that makes sense. I like PEBCAC. Problem exists between Kronos and KC. I wouldn't say that it's not that I don't like Kronos, it's that I just don't agree with a lot of the design philosophy is all. All right, let's go ahead and close everything down. Thank you, everyone, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along at home, you can always pre-order the game on handmadehero.org. It comes with a source code. We also have a forum site you can go to if you want to ask questions, a Patreon page you go to if you want to support the video series, a schedule bot you can use if you want to find out when we're going to be live, and an episode guide if you're trying to catch up on past stuff. I guess technically we did get the multi-sample working, in theory, with the caveat that it doesn't support sRGB. So I suppose next weekend, when we're back, I will be able to actually do the resolve and start actually using the alpha to coverage. In theory. But again, like everything else when you're programming on graphics APIs, it's just a complete crapshoot, and it's always unstable, it's always very buggy, it's always unpredictable, it oftentimes doesn't work on multiple machines the same way, and it's always really unsatisfying, which is why I don't like it. But we will try it anyway next weekend, so I hope to see you here for that, where we'll see if we can actually use the multi-sample stuff that in theory we now do have working properly, although again we can't seem to see any reason why sRGB doesn't work. I can only suspect that it's an AMD driver issue, although it may have something to do with the card being too old. So maybe I'll try to order a more modern card to stick in there so we can check it out. All right, that's about it. I hope to see you back here next week for that. Until then, have fun programming, everyone, and I will see you on the internet. Take it easy, everybody.